waves are? Any examples of electromagnetic waves that you know of?
Radio waves.
Radio waves, light, that's what your eyes are sensitive to. I mean, light, visible light, infrared light, UV light, X-rays, gamma rays, they're all electromagnetic waves. And like the name suggests, electromagnetic waves have both electric fields in them and magnetic fields in them. Okay, so let me show you a simulation. Here's a simulation. The E represents electric fields and B represents magnetic fields. So here's a light beam, and this is what is called a polarized light beam, but we won't worry about that right now. Polarization just means that electric fields vibrate in a single plane. That's polarized light. Generally, if you go outside in sunlight, it's an unpolarized beam, meaning it has rays that have electric fields in all vibrating in all planes. Okay. So here's an electromagnetic wave. So this wave contains both electric and magnetic fields. Okay. Now, if you were standing here and measuring electric and magnetic fields, here's how you would measure them. Okay. So the electric field is oscillating in one plane, the magnetic field is oscillating in a perpendicular plane, and the beam is traveling at you outside from the plane of the paper. So you see that at every instant, the electric field, magnetic field, and the direction of travel are perpendicular to each other. Okay, so this is an electromagnetic wave. Now, of course, this simulation is, it's a simulation. Just to make you understand stuff, for light, for visible light, the frequency is about 10 to the power of 15 hertz, meaning the electric field is oscillating 1,000 trillion times a second. Okay. And higher the energy of the electromagnetic wave, greater the frequency. Okay. So of course, you couldn't, if the simulation was true to reality, you would never see these oscillations. Okay. That, of course, is the wavelength of the wave, crest to crest distance, and so on. All right, so here's an electromagnetic wave. Let me show you different kinds of electromagnetic waves. So here's the electromagnetic spectrum. Okay, so here are all, see, this is arranged in terms of wavelength, shorter wavelengths on the right and longer wavelength on the left. Now this is arranged like funnily like that, and normally we have a longer wave, whatever parameter you're plotting against, that increases to the right. But the reason this is done so is because shorter wavelengths have more energy. And that is given by here. Higher frequencies, so higher frequencies have greater energy. Okay, so so let's look at these guys. So these are gamma rays, X-rays, visible light, radar. For radar, you use microwaves. These are infrared wavelengths. See, visible light, the sensors that you're born with, your two eyes, can only sense this narrow band in the entire electromagnetic spectrum. Okay. You can feel infrared waves, and of course, UV light will damage your eyes. But so your sensors for electromagnetic waves, your eyes detect a very narrow band of electromagnetic waves. Okay. And radar, microwaves, FM radio, AM radio. Okay, so these are all electromagnetic waves, and that's what we're going to study. Okay. All these different types of waves in vacuum travel at the same speed, and that is 3 times 10 to the 8 meters per second. Okay, so the speed of all these electromagnetic waves. this is this speed is an important enough speed in physics that it's given its own symbol. C is the symbol used for the speed of electromagnetic waves in vacuum, and it's 3 × 10⁸ meters per second. Okay, and they all travel at the same speed in vacuum. In different media, their speeds might be different. Will be different. So, for instance, rainbows wouldn't be possible if all the visible wavelengths travel at the same speed in water. Okay, so raindrops is what disperse the different colors. But anyway, we won't get into that. So this is the speed of light in vacuum, and what was it? And nothing travels faster than this thing, this speed. Okay, so this is a very important speed. All right. So now that you have a sense for electromagnetic waves, let's get started. Okay, so here's an interesting thing. Now, of course, we cannot, I mean, nowadays, wireless communication is such an integral part of our lives. It's interesting that Mr. Maxwell predicted the existence of electromagnetic waves. I mean, sunlight is an electromagnetic wave, so I mean, you're surrounded by electromagnetic waves, but we didn't know the nature of all that. He predicted the existence of electromagnetic waves using these 4 equations. Okay, so since we'll use these equations, let me write them down for you guys. I'll write them down on the chalkboard. So give me a second. Okay. All right. So here's a very interesting fact. Again, Mr. Maxwell, using these equations, 4 equations, he predicted the existence of electromagnetic waves. Okay. So they were theoretically predicted first using equations, and then people went looking for them. And so that's very interesting. And this happens in physics quite often. So Einstein's theory of relativity was prediction. I mean, it was a theory, and he said gravity must be this way. And so people went and looking for his predictions to confirm his predictions. And that's when experiments were designed to do that. All right, so anyway, so let's look at this interesting fact. All right, so here's the Lorenz's force law. What Lorenz's force law says is electric fields exert force on charges. So the force on a electric field is Q times E. A magnetic field also exerts a force on a moving charge. If the charge is moving, then the magnetic field will exert a force which is equal to that. Okay. So, by the way, let's go back to a simulation here. So, it turns out that, so here's a charge, and to produce electromagnetic fields, all you need to do is jiggle this charge. For instance, so by the way, you will use this in your simulation, in one of your experiments. I don't know if you've already done it. So this could be an electron. You grab hold of an electron and you jiggle it like that, and you will send out electromagnetic waves. And all waves carry energy. And look at this wave carrying energy. If you stick out a metal rod which has free charges, free electrons, this electric field will make these electrons jiggle. Okay. So this oscillating charge is sending out electromagnetic waves, and which is in turn making remote charges oscillate. Okay, so you stick out your antenna, you pick up the signal, and then you process the signal and get the information that was being sent from here. Okay, so now the reason I showed this is because so accelerating charges could emit electromagnetic waves. Now this is a general concept. So if you wanted to send out gravitational waves, you just have to grab hold of a mass and make it accelerate. So for instance, the Earth going around the sun, the Earth is accelerating, and so the Earth is emitting gravitational waves, except that the mass of the Earth is very small, and so those gravitational waves are very weak. If you want to send out strong gravitational waves, you would have to grab hold of a large black hole and then jiggle it. And of course, that's hard to do. So the only way that happens in nature is when two black holes are going around each other, and then they'll emit gravitational waves. All right. Anyway, that's what we detected about 3-4 years ago. All right. So here are electromagnetic waves. Okay. By the way, so in the lab, have you guys done the lab?
Not
Not yet.
this one.
Okay, so here's the radiated field. This is the static field. Charges produce electric and magnetic fields. So this field is not propagating. This part of the field is being propagated. So this is the radiated field. And you see when this thing is oscillating, these are electric fields and the electric fields are circular. Okay, the field lines are circular. If you take the tangent to these little vectors, the little vectors give you the electric field at a given location. Field lines are just the field lines are lines to which these electric field vectors are tangent to. So the field lines, the radiated field lines are circular around the oscillating charge. Okay. All right. All right, so what these equations tell you is charges produce electric fields, charges produce electric fields, moving charges produce magnetic fields, and so on. So charges produce electric and magnetic fields, and in turn, electric and magnetic fields influence charges. Okay. So by the way, between this equation and this equation, you can study all electromagnetic phenomena. You know? So if you become experts at this equation and this equation, then you can become a good electrical engineer. Okay. All right. So Maxwell's equations, along with Lorentz force law, completely describe all electromagnetic phenomena. Yeah. All right. So you saw that. So the propagating electromagnetic waves. We'll go over the next couple of slides quickly. But so you saw that this was the AC current, that was an AC current, was this charge oscillating like that, okay? And I'll show you how to make a charge oscillate like that in a little bit. But so when you apply an AC current to an antenna, the propagating field is like this. What this means is at this instant, at this point, the electric field is like that. At this, the electric field is there, and so on. So the electric field lines are circular, and the magnetic field lines are circular as well. Okay, and so at this location, the electric field oscillates back and forth like this. So we were looking at the electromagnetic ray traveling in this direction. That's what I showed you there. Where is that simulation? There. Okay. So that was the simulation. Or if you're very far from this antenna, this is how the wave will look like in all directions. Okay. It'll be a plane wave. But so this was the electromagnetic wave that was traveling. Okay. All right. So this What this equation shows you is the following. So let's get to my chalkboard. I don't want to spend too much time on this. So here are the four Maxwell's equations. What Maxwell did was he considered these equations in vacuum. In vacuum, this is 0, this term is 0. And what this equation tells you is curl B is equal to, and by the way, well, this is 1 over c squared, but I'll come to that in a second. So changing time varying electric fields produce magnetic fields. Okay. And that's what this diagram is showing you. Well, this one is showing you time varying magnetic fields producing electric fields. So it's this equation. Okay. Time varying magnetic fields are producing electric fields. And that's what this diagram shows you. So if magnetic fields increase in this direction, electric fields are produced like that. And we saw this in Faraday's law. This is Faraday's law. Okay. What this equation tells you is time varying electric fields produce magnetic fields. So if electric fields increase in this direction, magnetic fields are produced like so. Okay, and that's what this equation is telling you, which is this time varying electric fields. So this equation, time varying electric fields producing magnetic fields. Okay. All right, so these two diagrams are related to that. So what we're saying is, as this charge oscillates, the electric field is changing. Time varying electric fields are producing these magnetic fields. These magnetic fields in turn produce these electric fields, which in turn produce these electric fields, and so on. So the electric fields, as the wave travels, they are producing the electric and magnetic fields ahead. And that pattern propagates at the speed of light. Okay, that's what that's saying. Okay, so Maxwell, using the four equations shown, predicted the existence of electromagnetic waves. So if you carefully think about this, so this is important to understand, at least philosophically. So here are a bunch of mathematical equations, and you manipulate them and you predict the existence. You predict the existence of something that you weren't aware of. Okay. So I'll show you the derivation of that. Okay. And we'll keep it simple, but anyway, so here are the four Maxwell's equations. Okay. And we will need just one relationship. So here's, in Calc 3, you will learn this relationship, or maybe not. Anyway, what this equation tells you is curl of a vector is equal to the gradient of the divergence of the vector minus del square A, okay, of that vector. So since we'll use that, I will write it down. All right, so let me show you a derivation, okay? So here are the four Maxwell's equations, okay? And in vacuum, so in vacuum, what does vacuum mean? There's no matter there. So in vacuum, this term will be 0. This is charge density, and this is current density. This term will be 0. Okay. So in vacuum, divergence of electric field is 0. Okay. So if you went out in space between the sun and the earth, you can measure electric fields, and what you'll find is the electric field is such that the divergence of these electric field anywhere is 0. Okay. Divergence of magnetic field is 0, and that's true everywhere. Curl of the electric field is equal to minus del B by del T. Okay. And curl of B is equal to epsilon naught mu naught del E by del T. Okay. And it turns out that epsilon naught mu naught is related to the speed of light, c squared. Okay, so we are going to say del curl of B is equal to 1 over c squared del E by del T. Okay, so there are the four Maxwell's equations. Okay, now what I'm going to do is I'm going to derive the wave equation for you guys. Okay, again, don't get lost in some of the details. The point being, what we are going to show you is how, starting from an equation, you made a prediction, and that was later tested and verified. Okay. So this is the vector identity, vector field identity that we'll use, and you'll see this in Calc 3, hopefully, eventually. Is anybody taking Calc 3 right now? Has anybody seen this relationship?
We haven't gone over that yet.
What's that?
We haven't gone over that yet.
Okay. All right. So anyway, so curl of that. So let's start off with this equation. Okay. So curl of E is equal to minus del B by del T. Okay. Now what we'll do is we'll take the curl of that. Oops. Since we took the curl of that equation, we'll have to take the, and the curl and the time derivative are commutative, so you can switch their order. Okay. So everybody understand that? All I did was, here was this equation, here was that Maxwell's equation. Okay. And I took the curl of that, and so I took the curl of this. Now this, the curl of this vector from this identity we see is gradient of divergence of E, okay, minus del square E. And that's equal to minus del by del T. And for curl of B, see, curl of B, we'll use this equation as minus 1 squared del E by del T. Minus 1 c squared del E by del T. Okay. Now, in vacuum, divergence of E is 0. This term is 0. Okay. So this term is 0. So what we get is minus del square E equal to minus del, oops, I'll write the c squared, minus 1 over c squared del squared E by del T squared. Okay. And so I'll remove the minus sign. So del square E equal to 1 over c squared del E by del T squared. Okay. And this is the wave equation. And you can derive the magnetic field also will behave exactly the same equation. Okay. And this is the wave equation. So let me write the full-blown version of this. So what this del square operator means is del square by del x square plus del square by del y square plus del square by del z square. E is of course a function of x, y, z, and t plus, oops, is equal to 1 over c squared del E x, y, z, t del t squared. Okay, so there's the wave equation. Now it looks complicated, but we'll simplify things. Okay, we'll make life easy for ourselves in a second. All right, so what the wave equation is doing is It's relating the second spatial derivative of a function to the second time derivative of the function. Okay. And this is the wave equation. And so what have we done? So what did Maxwell do? Starting with these four equations and using some mathematical identities, what he realized was in vacuum, electric and magnetic fields will satisfy this equation, okay, which is this equation. And he solved this differential equation and he found solutions for them. And what he found was, so let's go ahead and do this. And so let's consider a function, electric field, that depends only on x and t, okay? Which is what you saw over here. Okay, so here's an electric field. Here's an example that depends only on x and t. So it depends on x, and if you stand at that location, that electric field depends on t. Okay, so you saw here are electric and magnetic fields that depend on x and t. Okay, so that's what we're going to do. So let's consider this. So when you do that, then this term will be 0, this term will be 0. So del square, del x square, ext 1 over c squared. Okay. And so Maxwell Maxwell's derived this equation. And then it's just a matter of solving this equation. And here is a solution, okay? We'll call it E now, okay? Sine 2 pi by lambda x minus 2 pi by f. Okay. So I've written it. So sine kx minus omega t. Okay. So here is the solution. And similarly, you can come up with a solution for a magnetic field, sine kx minus omega t. So this solution, this is a propagating wave. Okay. And this solution is exactly this fellow, this guy. Okay. So what we have seen is Maxwell using his equations. So he came up with this wave equation and he solved this wave equation, came up with the solution. So he's saying at his desk with his paper and pencil, hey, there must be propagating waves like this. There must be propagating waves like this. And so they went and looked for it. And Mr. Hertz was the one who first detected them. And here is Mr. Hertz's equipment. So here is Hertz's equipment where he detected the waves. Okay, so here is the circuit diagram for it. So here is an LC oscillator that you saw. So in the last class, this oscillates, but because of the presence of this resistance, in a real circuit you can't avoid resistance. This oscillator pumps energy into it. Okay. And also, even if you propagate electromagnetic waves. So this oscillator pumps energy into it. Its oscillation frequency matches the natural frequency of this oscillator. So this circuit is oscillating, and this is sort of an FM radio station right now. I mean, so this is how an FM or any radio station works. So here's the circuit, here's an oscillator attached to the circuit. This is coupled to another inductor. This inductor is coupled to another inductor, and that's a transformer. And here's the freestanding LC circuit. Okay. So energy is being pumped by this guy, which is transferred to this circuit. And this thing, here's an antenna, which is, here's the antenna like that. That antenna, radiated field, full field. Okay, so this is the electron oscillating, and there's the field radiated, and so uh, this is the capacitor, and as the field oscillates, as the charge oscillates, this is the radiated field, and this field is picked up by this LC circuit, okay, which is that antenna picking up the field. Okay. So that was Hertz's equipment. Okay. So here it is again. So this is the radiating capacitor, and here's this electromagnetic wave that was picked up. So for the first time, so this is how Hertz confirmed the prediction of Mr. Maxwell. Okay. All right, so we saw, okay, so let me summarize again. Okay. Maxwell, using his 4 equations, came up with the wave equation. Here's the wave equation, again, which is that equation. Again, the wave equation relates the second spatial derivative of a function to the second time derivative, partial time derivative to the same function, of the same function. Okay. And so if you consider a function that varies only with x and t, here's the wave equation in 2 dimensions, in one spatial and one time dimension. The solution to this equation is that, and that is a propagating wave. Okay. So this is what Maxwell predicted, and Mr. Hertz went and confirmed that. Okay. So that's the story. All right, what I'm going to do is I'm going to pause for a second